Seismic Attributes Part 3. As we understand that 3D seismic data is utilized to evaluate the attributes from seismic, we'll talk a little bit about how the acquisition takes place in case of 3D seismic. Now we know that in 3D seismic, the first design which has to be made is the bin size. And the bin size is a function of the minimum velocity in the layer, and also a function of the frequency, which is the maximum frequency and the maximum depth of the bed. In the seismic section shown in the left, it is a strike section taken from a 3D survey, and it is a vertical section from onshore Texas. The important point to be noted is that the bin has to be first decided. Once the bin is decided, twice the chosen bin size is the source and receiver station spacing. Now we know that on the top of the section we have the source points, and then on the y-axis we have the two-way time. The two-way time increases with depth. The second point which need to be looked into is the understanding on the number of source station. I will go back to the first slide and we will talk about that how to compute the number of source station per square kilometer. It is achieved if the fold to be achieved for the data is known, and the fold the available equipment can deal with. The number of stations per square kilometer allows computation of the source line spacing. NS is the shots per square kilometer is a function of F into 10 to the power 6 divided by R into Bx and By, where Ns is the shots per square kilometer, F is the desired fold of the bins, R is the number of channels on the field equipment, and B is the subsurface bin size. The next thing which we require to understand is the source line space, and in this case we will find the SLX is equal to 10 to the power 6 divided by Bx into Nx, where Ns is the shots per square kilometer and Bx is the bin size in the x direction. If it is a square bin, Bx is equal to By. Then we need to compute receiver line spacing, and in this case the new information required is the minimum offset and offset ranges. We calculate that as A is equal to C square minus B square whole to the power half, where A is the receiver line spacing, C is the largest minimum offset within a short bin, and B is the source line spacing. The last step is to calculate the number of receiver lines allowed by the field equipment, constrained by the required offset range. The result is a template. The offset constraint may be evaluated by Pythagoras theorem as h equal to x square plus y square whole to the power half, where x is equal to length of receiver line minus source line shift. Y is the distance from the short to last receiver, and we need to decide on the x and y roll alongs. If we can do a good survey with a good amount of frequency required for mapping, if there is a continuity in the horizons which we would like to map, in this case the two important horizons which were of interest to us are shown by green arrows here. Then we will be able to make a good cube which has strong inlines and cross lines. Now the vertical section from 3D survey is now converted on the right to a reflection strength display of same section, and we can see that features dipping west which are thought to be depositional clinoform. So we were able to map the depositional clinoform and also find out the base of the depositional clinoform. The depositional clinoform between the green arrows actually are stacked to each other. However, at places they are elongated and they are separated from each other. So as we know from the sequence stratigraphy that these are probably from the low strand system track. We go to the next slide and we can see on the left amplitude version of enhanced vertical line. It's a cross line, as I have told, showing west dipping alignments of high amplitude which give rise to suspected clinoforms. We could map the clinoform. However, at the green level, we could find a horizon slice, and we prepared a horizon slice in order to understand the reflection strength showing spatial patterns of suspected clinoforms. The horizon that was tracked is indicated by the green arrow. Extract of reflection strength at the position of the green arrow need to be noted. As we see this diagram, we can understand that there is a four-way closure to the southeast of this horizon slice, and then there are two nosing features, one on the northwest and one on the southwest. We go to the next slide, in which we have tried to understand the seismic energy over the reservoir interval from North Sea. High energy is indicated sand in a shale dominated environment. Look at the warm colors, that is in red. The warm color shows the zone of maximum seismic energy, whereas the cool color shows the area of lower seismic energy. Now, all of us know that energy is equal to the amplitude square and is a very important phenomena to be understood because it helps us to decipher the channels and also the structural pattern. It also gives an idea where there are disruptions or the faults are present. We can see a fault shown in black at the eastern side of the map. We go into the next slide where we are trying to understand the number of zero crossings over reservoir interval from the North Sea. The interval has been shown in the vertical section between the two green arrows. The fault can be seen once again, which is a dark blue patch, and the zone of maximum zero crossing between east and west fault is also seen, which is marked by an arrow, which is a white color arrow. Now, all of us know that when we map a 2D seismic section or a 3D seismic cube or a 3D seismic section, we either track manually or auto track, which is done automatically in the software used in order to understand the reservoir continuity, in order to understand the horizon which is of importance to us. We have to map either on the peak or on the trough or on the zero crossing. This map indicates layering and also serves as a quality control filter for horizon mixed peak. Note the zone of maximum zero crossing between east-west fault, which I have already told, and that should be kept in mind while we take this attribute of zero crossings in our understanding of the structural alignment, the fault disposition, and hydrocarbon presence. In the next slide, we can see energy half time map over reservoir interval from North Sea. Look at the blue spot on the west. It is the sand body formation. This is densely blue, so it is a continuous sheet sand at the base of the formation. Observe that we are trying to understand attributes from the various type of attributes which has been talked about, and we need to consult and consider all these type of attributes in order to make conclusions of the presence of hydrocarbon, the structural disposition, and the fault placement. Now, energy half time map is one of the attributes which is run over reservoir interval, and this example is taken from North Sea, indicating vertical distribution of sands within the reservoir. The wave shape is also very important. As I told you that wave shape are classified on the seismic traces. We know that seismic traces is actually a wiggle trace. In this case, we can see the wiggle trace from left to right, and wave shape depicting peak, zero crossing and trough is an important attribute. Wave shape classification of seismic traces over an interval of 100 milliseconds is shown here. The classification uses neural network pattern recognition technology in order to understand where there is peaking and where there is a trough. You can see that the peaks which were there in the left has gone and made it into a trough at 10, 11 and 12. So that is an indication that there is a polarity reversal. A polarity reversal talks about the presence of gas. So this attribute is mostly utilized for understanding the gas presence. In the next slide, we can see a seismic phases map showing channel system where colors indicate the 12 different wave shapes which we have talked about in the previous slide. The classification gives us the shape run over restricted area but with same number of classes shows phases along the channel. And as I go to my next slide, we can talk about wave shape run over whole area which shows a channel. Wave shape run over restricted area but with same number of classes shows phases along the channel. Now this channel is cut out from the map which we have seen on the left, and only the meandering channel has been brought out beautifully by Paradigm Geophysical in this particular example. And we all know that the channels plays a very important role in hydrocarbon exploration, and mapping channels are important whether we are on the slope faces or whether we are on the floor faces. So that has to be understood how the neritic diagram looks like and which section of the neritic diagram we are looking for channels. Now the channels can be cut and fill structure where the base material is cut by scouring and then new material is deposited. You have seen in your geography classes in class 12 that meandering channel creates a complex system which is a channel levee system, and we have seen the formation of Oxbow Lake in case of the channel levee system. Understanding the channel levee system is important aspect in hydrocarbon exploration, and the lobes which are created due to the channels also can be mapped from the attribute analysis. Here is an example where a loop area and arc length is used for understanding one of the attributes which is the average porosity. The average porosity gives an idea of how much porosity is there in the reservoir and how much it is hydrocarbon bearing. You also need to understand the effective porosity, and the attribute maps helps you to understand whether the porosity is high or whether the porosity is low. The porosity is given as a percentage which is a delta V by the bulk volume. In this case, the red color shows that the highest average porosity is 20 and the lowest average porosity is 0, which is shown by blue color. When we impose the porosity map on the time structure, we can understand in conjunction with the time structure which is the place where we have high porosity. In this case, the red and yellow are the high porosity sections which can be found out. And when we talk about the channels, we can actually see that they are dissociated meandering channels with two lobe system. Both the lobes are shown with yellow and red. One of the lobe is seen on the west and another lobe is seen in the east. Loop area talks about reflection amplitude. We can see here that the amplitude is maximum and a window has been considered which is a time window. So it can be done on the depth window or on the two-way time window. The maximum amplitude is utilized to understand the energy spectrum also, because square of amplitude will give you the energy contained in these reservoirs. Another important attribute which has to be understood is arc length. arc length or reflection heterogeneity was used to map depositional phases. Notice in the left steeply dipping parallel bedding overbank sands with gas. On the right, the green color shows the slumps, which is more on the northeast. In the right, we have channel levy complex, and which is in red, and I was talking about the fan lobes. The fan lobes need to be found out, and also the internal structuring has to be understood, that whether it is a fining upward sequence or whether it is a coarsening upward sequence. So the advantage of 3D is that this need to be looked into both in inline and cross line, and maybe we can prepare couple of attributes like vertical stacking or chair cut display in order to see how this attribute plays a very important role in order to understand the lobes which are there and which of these lobes can be hydrocarbon bearing. Testing need to be done on any attribute. Drilling of wells is important in order to establish attributes, and if that well at that particular horizon of interest shows hydrocarbon, we can drill appraisal wells and development wells in order to delineate the extent of the channel, and some risk is involved because there may not be any structural component. It may be based on sand and how the sand has been deposited. Many of times we have seen that there are braided channels, and in these braided channels we can actually see shore parallel sand which are of importance from the hydrocarbon point of view, and these are cut by tidal inlets which are the cheniers. So barrier bars and cheniers had to be understood in order to establish the relationship of attributes with the hydrocarbon presence. Amplitude, instantaneous frequency, and arc length, which is nothing but reflection heterogeneity, are used for mapping depositional phases. Another important aspect which need to be understood is how various type of frequency attributes are important in delineating phases, in displaying the same type of reservoir geometry in various shades, and in order to understand the faults which are synthetic and which are also antithetic. In this case, we can see a graben at the center and structural highs on the two sides of the fault. The fault bounds the graben and the structural highs are there on the northeast and also on the northwest. We can see that various type of spectrums has been used. The first one is a spectral frequency. The second one is the first dominant frequency. On the third map, we can see the second dominant frequency. On the fourth map, we can see the slope spectral frequency. We can also use the attribute of average instantaneous frequency and slope instantaneous frequency. We also understand that if amplitude is there and we understand the instantaneous frequency, whether it is the first order or the second order instantaneous frequency, amplitude squared by root over instantaneous frequency gives us a sweetness map. Sweetness is an important aspect in the attribute analysis in order to understand the phases which are hydrocarbon bearing. We can also see that various type of amplitude attributes or energy attributes can be used over the same area, over the same interval to understand hydrocarbon presence. In this case, we can see that there is an energy half time attribute, then there is a slope reflection strength, we can use a ratio attribute, we can use an average absolute amplitude, and also we can use an RMS amplitude in order to understand the structural disposition and also superimpose the attributes on structural maps. Average instantaneous frequency map from southern Argentina shows the presence of gas based on the instantaneous frequency. Now you can see there are two faults once again. The faults are marked by green. Two major faults which is there, one on the center part of the map and one on the left part of the map are the major faults. The arrows indicate the wells which are the production wells clustered in the area. The average instantaneous frequency, which is red in color, is high frequency, and which is blue in color is low frequency. So in the central part between the fault we have low frequency. On the flank part we have high frequency, which is shown by yellow and darkish yellow, which gives us that there is a possibility of gas presence, and it has been established by the production well. The number of zero crossing map from southern Argentina also shows the same type of feature. We can see that at the central part we have the low zero crossing and we have the high zero crossing on the western side of the green fault and on the eastern side of the next green fault. And once again we have shown the production well, which is a clustered in the areas indicated by the red arrow, and we have seen that the mapping has helped us to drill those wells and see that production happens. I should tell you that understanding attribute has limitations, because same attribute or different attribute which should be considered should be chosen very carefully. However, the four main attributes, that is attenuation, amplitude, frequency and sweetness, should always be studied in conjunction in order to see where there is a possibility of hydrocarbon present. Attributes do not mean that there is a 100% chance of hydrocarbon presence, so it has to be used in caution. Some exploratory well need to be drilled first in order to validate the attribute aspect, and based on the well and the horizon of interest where we can get hydrocarbon, we'll try to see the same type of attribute in other part of the lease which has been given to us by DGH or any of the authority, and we should look into these type of features which are stratigraphic feature or stratistructural features having hydrocarbon, bounded by fault, controlled by fault, which may be faults which are sealing fault or leaking fault, has to be established in order to take help of the attributes. We'll see more on the attributes in the next lecture. We need to practice and understand these attributes which I have talked about today. To summarize, we have talked about attributes on the vertical section. We have talked about attributes on the maps. We have discussed on horizon slice, which plays a very important aspect in order to slice the horizon to see how the structural pattern looks like and how the spatial patterns of successful or suspected clinoforms are there. Seismic energy, number of zero crossing, wave shape, seismic phases map, channels understanding using zero crossings, using the amplitude strength is also very important. Porosity determination from the seismic is a new technique which is imposed and superimposed on time structure map in order to understand the areas of high porosity and low porosity. Reflection heterogeneity and use of different frequency and amplitude attribute together will give us a very good understanding of the hydrocarbon presence. With this, we end the presentation today, and we look forward to more understanding of attributes in the next video.